All right, we're going to look at the most missed questions from last night's homework set. I think this was a pretty tough homework set, equally as tough as the word problems the night before. So this first problem says, Cassandra finds a treasure chest packed with metallic coins. The chest has a volume of 0.25 meters cubed, and the coins have a combined mass of 4,825 kilograms. Hoping to find gold, she calculates the density to determine the metal of the coins. All right, so first thing we look at is we want density, and I always look to units. Units for density are a mass per a volume. All right, and in this one it's meters and kilograms, so we're looking at kilograms per meters cubed. So when I'm trying to find the density, what I'm really going to do is I'm just going to find a kilogram measurement, which we know that we have 4,825 for the mass. All right, and that's in kilograms. And we're going to divide that by a volume, which in this case is 0.25. All right, meters cubed. Now, if I take the 4,825 and I divide that by the 0.25, I end up at 19,300, and that would be kilograms per meter cubed. All right, so that is the density of the metallic objects, the coins. And I look to my list, and it looks like the only one with that level of density is actually going to be gold. All right, so my correct answer on that one is D. All right, I hope that helps for the first one. Let's take a look at the next one. So the next one says, and this is a weird one, says when the weight of an object equals the weight of the water displaced, all right, or pushed away by an object, the object is naturally buoyant, all right, and easy to lift to the surface. So what you want is you want the weight of the object and the weight of the water pushed away to be equal in order to do this. Right? So a sailboat sank to the bottom of the ocean. The majority of the boat's weight is from the quarter meter cubed of lead in the keel. The density of the lead is 1,000. Right, kilograms per meter cubed. And we know that was roughly from the 1/4 or 0.25 meters cubed. All right, so we know those two are connected to each other. And it says the density of seawater. All right, so this was our boat back here. And then seawater density is 1,000 kilograms per meter cubed. All right, it says because gravity is pretty much the same everywhere on Earth, the weight of the sailboat can be assumed to be approximately equal to its mass. So we're not going to worry about a difference between weight and mass here. We're going to consider them basically as the same. That will hold true for virtually all the problems that we deal with. So this says in cubic meters, what is the total volume of seawater needing to be displaced in order to lift the sailboat to the surface? All right, so the first thing that we're going to have to do is we're going to have to find out how to connect these two pieces of information. All right, so if I look at this first one, I have 11,000, all right, and that's kilograms per meter cubed. All right, and then I have a meters cubed. So if I multiply by the 1/4 meters cubed, my meters cubes would cancel. And if I take 11,000 and I divide that by 4, I get 2750. So 2,500. And the only units that would be left would be kilograms. All right, so roughly we're going to say that the boat weighs approximately 27,500. All right, now we're going to look over here. If we take the density of the water times the volume of the water, right, that would give us the weight of the water. All right, so density of water times the volume of water gives us the weight of the water. So we know one component of that. We know the 1,000, the density, kilograms per meter cubed. All right, but we don't know the volume of water that we need to move. All right, so if I take and I set up this equation where those two are equal, because that's what they told us, that those two have to be equal in order for us to have a neutrally buoyant object. So I'm going to divide by the 2,000 on each side. Or sorry, divide by the 1,000 on each side. And if I divide each side by the 1,000, and the units on that are kilograms per meter cubed, all right, I end up at, if I move my decimal place, 1, 2, 3, a 2.75 equals the volume of the water. But then I need to find out what units that would be. So I'm going to investigate the units, and I'm going to pull those over here to the side to do that. I have kilograms over kilograms per meter cubed. That's equivalent to kilograms times the reciprocal, meters cubed over kilograms. Kilograms cancel, I'm left with meters cubed. So I'm looking at a volume of water that needs to be moved of 2.75 cubic meters. All right, and that's the amount of water that would need to be displaced to lift the sailboat to the surface. All right, I hope that helped on that one. All right, for the next problem that was commonly missed, it says a soda company wants to efficiently pack 9 cans of soda in one box. Each soda has a radius of r. What is the ratio of the height of the rectangle pack H1 to the height of the parallelogram pack H2? All right, so H1, if I look at this, I've got 1, 2, 3, 4, 5, 6 radiuses. All right, so H1 equals 6 R's. Now, when I look at H2, all right, I'm going to think about 2 triangles and 2 radii. All right, so for H2, first thing I'm going to add on are the 2 radii I have, which are from the top to the top of that diamond we have, and then from the bottom of the diamond to the bottom. All right, so I'm going to do 2r for that, plus now I need to add on 2 of the height of one of these red triangles. All right, so when I look at that red triangle, and I'm going to pull that off to the side here, all right, I know that I've got 2r on each side. All right, I know that this is a equilateral triangle because this side would be 2r as well. All right, so if I cut it in half, I have a 30, 60, 90, and I have r and r root 3. All right, so if I run through, if I think about the height of that triangle, the height of that triangle is r root 3. All right, so we have a height of r root 3, and the base is 2r. All right, but we're just trying to find the height of this, so we're actually not going to worry about that base. So I'm going to bring this back over, and I've got H2 equals 2r plus, right, 2 of these heights of this triangle, so 2 times r root 3. All right, I'm going to clean it up a little bit. 2r plus 2 root 3 times r, and I'm going to choose to factor an r out. So I've got 2 plus 2 root 3 times r. All right, so that's going to be my height of H2. Now we want to find the ratio of these two. So if I take the ratio of height 1 to height 2, I have 6r over 2 plus 2 root 3 all times r. So right out of the gates I can cancel the r's. I have 6 over 2 plus 2 root 3. I lost my 2 there. There we go. All right, then I can factor a 2 out of the top and 2 out of the bottom. So I have 2 times 3 on the top. On the bottom I have 2 times 1 plus root 3. All right, we can cancel the 2's. And then when I do that, I'm down to 3 over 1 plus root 3. 3 over 1 plus root 3, which corresponds to answer B. All right, so the ratio of the height of the rectangle to that is 3 over 1 plus root 3.